Have you ever pondered the nature of time and space? What if the way we perceive them isn't the only way they exist? Imagine you're aboard a spaceship, zipping through the cosmos at a significant fraction of the speed of light. Let's call this speed v. From your perspective, everything seems perfectly normal. Your clock ticks away the seconds just as it always has, and the length of the rod attached to your ship seems unchanged. But what if I told you from an observer on Earth your clock is ticking slower and that rod appears shorter? Bizarre, isn't it? This isn't a plot from a science fiction novel, but the reality of our universe as described by Einstein's theory of relativity. It's a world where time can dilate and space can contract. Let's dive into the world of relativity and explore how time and space behave when we're moving at nearly the speed of light. Imagine you're aboard a spaceship traveling at a significant fraction of the speed of light. You're cruising through the cosmos with your trusty clock, ticking away seconds just as it always has. From your perspective, everything's business as usual. Time in your spaceship is flowing as it always does, but let's switch gears and zoom back to Earth. From here, watching your spaceship zip through space at such a high speed, things start to get a little peculiar. According to our friend Einstein and his theory of relativity, time isn't constant, it's relative, and it depends on the observer's motion. So from the Earth observer's perspective, it seems like time on your spaceship is passing more slowly. Your clock is ticking, but those ticks are taking just a bit longer. This is what we call time dilation. It's one of those mind-bending consequences of relativity. You see, as you move faster and faster, approaching that constant speed of light, your time begins to stretch out, to dilate, if viewed from a stationary observer like Earth. In essence, from our perspective, you're moving into the future at a slower pace than we are. But why does this happen? Well, it's because the speed of light is unchanging for all observers, regardless of their motion. As you speed up, your time appears to slow down from our viewpoint back on Earth. It's a fascinating and somewhat counterintuitive effect, but it's been confirmed by countless experiments. So, as you're out there in your spaceship cruising near the speed of light, time for you is just fine, ticking away as it always has. But for us on Earth, it's as if we've hit the slow motion button on your journey. This is the fascinating concept of time dilation. But what about space? How does it behave at such high speeds? Well, for that, we'll need to delve into the equally intriguing concept of length contraction. But that's a tale for the next scene. Now consider a rod attached to the spaceship. What would its length look like from Earth? As we speed through space, things inside our spaceship, including the rod, appear completely normal. You measure the rod, and it's exactly as long as you'd expect. But let's shift perspectives and consider an observer on Earth. As they watch your spaceship zoom away, they don't see the rod as you do. Instead, they witness an intriguing phenomenon. As your spaceship accelerates, the rod, as seen from Earth, appears shorter. The faster you go, the more the rod seems to shrink. This isn't an optical illusion or a trick of light. The rod's length, as measured from Earth, genuinely appears to contract. This phenomenon is known as length contraction, but hold on a second, you might be wondering, if I'm aboard the spaceship, why don't I notice the rod shrinking? Well, that's the fascinating part. You, the spaceship, and the rod are all moving together. From your perspective, everything inside the spaceship remains the same. The contraction is only apparent to an observer who is stationary relative to your motion, such as our observer back on Earth. So while on board, you might measure the rod and find it to be, say, 1 meter long. But an observer on Earth using their own meter stick and watching you whiz by would measure the rod to be less than 1 meter. The faster you're traveling, the shorter the rod appears. This contraction isn't limited to just rods or even physical objects. It applies to all lengths measured in the direction of motion. In other words, the spaceship itself, as viewed from Earth, would also appear contracted. So we've established that, from your perspective aboard the spaceship, time seems to tick normally and lengths appear unchanged. However, from Earth, time on the spaceship seems to slow down and lengths in the direction of motion appear contracted. This is the equally intriguing concept of length contraction, but why do these effects occur? These effects might seem bizarre, but they stem from a simple yet profound principle. You see, the heart of these phenomena, time dilation and length contraction, lies in the constancy of light's speed. Yes, you heard it right. The speed of light is the same for all observers, regardless of their motion or the motion of the source of the light. This fundamental postulate of Einstein's theory of relativity is what gives rise to these seemingly strange effects. Now, you might be wondering, how does the constancy of light's speed relate to time and length behaving differently? Well, let's delve a little deeper. Imagine you're aboard that spaceship again, traveling at a significant fraction of the speed of light, which, by the way, we're calling v. From your perspective, inside the spaceship, everything feels normal. Your clock ticks away the seconds just like it always has, and the rod attached to the spaceship appears its regular length. But for an observer back on Earth, things are different. To them, your clock seems to be ticking slower than normal, and that rod on your spaceship appears shorter. Why? Because the speed of light is the same for both you on the spaceship and the observer on Earth. As you approach the speed of light, time for you on the spaceship seems to slow down from an Earth observer's perspective. Similarly, lengths as measured from Earth appear contracted in the direction of your motion. In essence, time dilation and length contraction are the universe's way of ensuring that no matter where you are, no matter how fast you're moving, the speed of light remains constant. They're not mere quirks of physics, but essential adjustments that the universe makes to keep the speed of light unchanging for all observers. So, the constancy of light speed is the key to understanding these phenomena. But how can we visualize this? Stick around, and you'll find out in the next scene. Let's conduct a couple of thought experiments to better grasp these concepts. Imagine you're aboard your spaceship, armed with a light clock. This is a simple device, a clock that measures time by bouncing light between two mirrors. As you accelerate through space, you notice the light's path between the mirrors remains unchanged. It's simply bouncing up and down, marking the seconds as they pass. But let's shift the perspective. Back on Earth, observers are watching your spaceship's light clock. From their viewpoint, the light isn't just bouncing up and down. Instead, it's taking a longer, diagonal path between the mirrors. Why? Because while the light is in transit, the spaceship is moving forward, causing the light to traverse a wider path. This longer path means it takes more time for the light to bounce between the mirrors. Hence, time appears to be dilating from Earth's perspective. Now, let's consider another experiment. Imagine you have a ruler attached to the side of your spaceship. From your vantage point aboard the vessel, the ruler's length is consistent with what you've always known it to be. It's a standard ruler, after all. However, it's a different story for the Earth observers. As the spaceship's speed increases, the ruler appears shorter to them. It's not because the ruler itself is physically changing. Instead, it's a result of relativity. The distance the light travels to convey the measurement of the ruler to the Earth observer is affected by your high speed. Consequently, the ruler seems contracted in length. These experiments offer a glimpse into the strange yet fascinating world of relativity. They illustrate how Einstein's theories of time dilation and length contraction play out in the real world, or rather the universe. Even though we're dealing with concepts that challenge our everyday experiences, these thought experiments give us a tangible way to understand the extraordinary workings of time and space. So the faster you go, the more time appears to slow down, and lengths appear contracted when observed from a stationary perspective. This is not science fiction, but a fundamental aspect of our reality. As explained by Einstein's theory of relativity, it's a concept that may seem counterintuitive, even mind-bending. Yet it's backed by solid experimental evidence and is integral to our grasp of time and space. Time dilation and length contraction are not mere theoretical constructs, but observable phenomena. They are the universe's way of ensuring that the speed of light remains constant for all observers, regardless of their relative motion. It's a cosmic speed limit that governs the fundamental nature of our reality. So, as we venture into the cosmos, we're not just exploring new frontiers in space, but in time as well. Through Einstein's relativity, we've journeyed into the heart of time and space, revealing their flexible nature under extreme speeds. It's a journey that continues to inspire and challenge our understanding of the universe.